Okay, the purpose of this video is to cover the second half of chapter 5, which introduces covalent compounds. So we're going to talk about the nature of covalent compounds, what they are. We're going to talk about ways of representing covalent compounds and naming covalent compounds. So that's where we're going, and let's get started. All right. So covalent compounds, the key feature of covalent compounds is atoms sharing electrons. So while ionic compounds are held together because of the attraction between positive and negatively charged ions, the key feature of covalent compounds is atoms share electrons. Okay. So they're composed of atoms of different elements or the same element. And the thing that forms the bond is not an electric attraction between a positively negatively charged ion. The thing that forms the bond is much like these two dogs here who are each holding on to an end of the same bone. They don't look like they're sharing here, but they are actually sharing those bones. So we have, what happens is we have valence electrons in our atom that are unpaired, right? So in atom A here, we have one non-metal atom that has one electron and that is unpaired in its valence shell. And atom B, which can be another non-metal or metalloid, also has one unpaired electron. And what happens is they will share those electrons, and that forms what we call a covalent bond. Okay, so this is a covalent bond. And we call that molecule where these atoms are now stuck together because they're sharing those valence electrons, a covalent molecule. And you'll notice that when they share the electrons, okay, now atom A actually has 8 electrons around it, and atom B also has 8 electrons around it. Okay, so there are 2 types of covalent compounds. We have molecular compounds, which is what we are going to primarily focus on, and then things called network covalent compounds that are much larger kind of arrays of bonded molecules. All right, so a molecular compound, okay, is composed of molecules that are always composed of kind of the same number and types of elements. Okay, so a molecule of water, okay, always has 2 hydrogens and bonded to 1 oxygen. All right, and so the formula for this, if we go for our, chemical formulas where we put the symbol for the element, okay, and the symbol for the other element, and then we use subscripts to tell us how many of each type of element we have. So that would be H2O. All right, now for a molecular compound, okay, we're going to have a certain ratio of the different elements in our compound. So if we look at this compound over on the right, we have 3 carbons, okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogens, and we have 1 oxygen. Okay, so we could write the formula for our molecule based on, again, the number and types of atoms that are there. And so every time we have atoms that are, bonded in this way, we have a molecule of water. And we can have a collection of molecules of water, right? So this is 1 water molecule. And this is a collection of water molecules. All All right. So I mentioned there's something called a network covalent compound. All right. And so what network covalent compounds are when we have a very large number of atoms and we have different elements and they're bonded again just like in water we have the oxygen and the hydrogen sharing electrons. They're going to be bonded by shared electrons. However, we get much larger extended structures, and this is an example right here. That this one is showing the label got cut off. It's silicon dioxide, also known as sand, right? So we have large extended networks instead of individually bonded things, okay, like the water molecule. All right. So our covalent compounds, we have different ways of representing the identity of the compound. So the purpose of this slide is explaining the different ways of representing the identity or communicating the identity of a covalent compound. Okay, so we have something that's called the molecular formula. Okay, and that's what we wrote when we wrote our, for example, our H2O. Okay, or with the other example we had C3H8O, right? So C3H8O. All right, now the empirical formula is going to be related to the molecular formula, but it's going to give us the simplest integer ratio of atoms of each element. So what you could do is you could, let's say we had a compound that had 6 carbons and, 16 hydrogens and 2 oxygens, okay? That actually could be simplified, right? All I did here was I had multiplied this by 2. So I could have a larger compound, okay, that has the same empirical formula. So this right here could be the molecular formula for the molecule I showed on the previous slide, or it could be the empirical formula for this, okay? So this is just this could, molecular formulas are sometimes a multiple of an empirical formula. All right, and so these are, again, these are kind of what you would use in text, right? In or writing, okay? Because they use our symbols, and they're not, just our alphanumeric symbols, okay? These ones over here, the structural formula and the models, okay? These are more visual representations, okay? They're going to be pictures or three-dimensional models, okay? Pictures or 3D models. And you used some of those three-dimensional models that were on the computer in lab last week, or in the previous week's lab. So these are going to show not just what atoms are there, but they show who's bonded to who, and then they can show the shape. Okay, so our molecular and empirical formula only tell us what's there and how many are there, and then the structural and the models will show us how atoms are arranged. Okay, who's bonded to who and where they go in space. Oops, that is not turning the page. This is turning the page. Okay, so we've already written the molecular formulas for these two compounds, right? So this was our H2O, and this was our C3H, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and O, right? So subscripts tell the number of atoms of that element. Okay. Now, so remember, again, case matters. So, I could write, let me see if there's, I could write CO, okay, both capital, or I could write C little o. This is carbon and oxygen. This is a different element. This is that's the symbol for cobalt. So case matters. And also, when I say subscripts, okay, I mean, we don't write this as C3H8O. Okay, that when we use numbers and they are as large as the element symbols, they mean something different as when they are subscripted. So we don't do this, we do this, and we write those numbers as subscripts, smaller and below the element symbol. So not this, but this. Okay? All right, so that is the molecular formula. And as I've said before, an empirical formula, okay, is the key is it's the simplest integer ratio of atoms of each element. So we're going to start with this compound shown on the screen here, and we're going to write the molecular formula, which is all atoms accounted for. Okay. So we've got carbons and hydrogens in our compound, and we've got 1, 2, 3, 4 carbons, so we'll subscript 4, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. This is what we call the molecular formula. All the atoms are shown in the formula. But you'll notice that, these are a multiple of, 2, right? So so the empirical formula, I can write this kind of in a simpler way. And the empirical formula is more a reflection of if I took a sample of this material, okay, and I figured out how much carbon there was and how much hydrogen there was in the compound on a relative basis, what would I find? So if I took all the carbon and weighed it, and took all the hydrogen and weighed it, and came up with kind of the simplest ratio of atoms, okay? So this doesn't account for all atoms. It gives the lowest ratio, of atoms of each element, okay? So I would have to find some common denominator. So this one's fairly easy. If I divide both subscripts by 2, so I'm starting with C4H10, divide both subscripts by a common denominator, in this case 2, then I would have C2H5, okay? Oopsie, sorry. So this tells you that, for every 2 carbon atoms, I have 5 hydrogens in this material. And if I were to, again, break this up into carbon and hydrogen and weigh it in the lab, that's what I would find. I wouldn't find, 4 moles of carbon and 10 moles of hydrogen. It would break down into a lower ratio, okay? So this really tells you, the thing that empirical formula tells you is the relative amounts of each element. Okay? That is characteristic of that particular compound. So several compounds may have the same empirical formula. Okay, so that's, but they'll have different molecular formulas if they're different molecules. Okay. All right, so molecular and empirical formulas can be the same. Okay, so often the same, molecular and empirical. And an easy way to see this is to look for an odd number of atoms. So let's look at this molecule here, and let's do the molecular formula. So we have 3 carbons, and then we have how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1 oxygen. Okay, that oxygen right there. So if we were to look at the empirical formula for this, let's look at these numbers here. Is there a number that we can divide these 3 numbers by that would, that would create integer values? Okay. Now notice over here, okay, I'm going to just highlight over here. If there's only one, okay, we don't put ones in formulas. Okay, we assume if there's no subscript, then there's only one of that atom there. Okay, so we cannot, there's nothing we can divide by, right? If we divide by anything, we'll wind up getting a fraction. So the empirical formula for this is C3H80. Okay, all right. So that is the molecular versus the empirical formula. Okay, so let's talk about isomers. Okay, so and structural formulas. So a structural formula shows connections. Okay, so it shows connections between our atoms, right? And so what you see is you're going to have one line. It means 2 electrons are shared. Okay, so that's what we call it. So each atom contributes 1 electron to the bond. Okay, so in this example right here, this bond that I'm coloring in right here, that means carbon and hydrogen each give 1 of their electrons to the bond. Okay, so that's what 1 line means. 2 lines means 4 electrons are shared because each line is 2 electrons. Okay, and that's called a double bond. And then 3 lines, and this is as high as we go with covalent bonds, means 6 electrons are shared, and that's called a triple bond. Okay. All right, so this is the structural formula. It shows you which atoms are bonded to which. Okay, and this is an example of an alcohol compound because it has this OH here. Now there are other ways of arranging these atoms. So I could do something like this. I have my 4 carbons, and instead of having the oxygen bonded to this carbon right here, I could have that oxygen bonded to the second carbon in from the right. So I have the same chemical formula in terms of molecular and empirical formula, right? So let's write our molecular formula. For this. Okay, so this would be C4H8, 9, 10, and then O. Okay. Our empirical formula, is it going to be the same or is it going to be different? Well, 4 and 10 we could divide by 2 and we could have C2H5, but the 1 for the oxygen we could not, right? So the empirical formula for this is just going to be the same as the molecular formula because we have one of our elements has an odd numbered subscript. And even though we don't show the 1, okay, we understand that the subscript for that is a 1. Okay? All right, so we've got the molecular and empirical formula. It is the same molecular and empirical formula for both of these compounds, okay? But they are not, I mean, you can look at them and they're not the same thing, right? They don't have the same atoms bonded to each other. We've got our oxygen hanging off of the end of the molecule in one place and in the middle of the molecule in the other. And so these are called isomers, okay? So there's different types of isomers, and if you take organic chemistry, you'll learn a lot more than you ever want to know about isomers. But what isomers are they're a different way of arranging the same atoms, okay? And again, we have different types of isomers, so sometimes, you know, the bonding is different, and sometimes it's just the shape and space that's different. All right, so structural formulas. Okay, we have the larger your molecule gets. Okay, so we use something called condensed formulas. So larger molecules take more space to represent. Oopsie. So we come up with shorthands or further ways of representing them succinctly. So we use what's called shorthand. So it's an easier, a briefer way of designating the molecule, okay, of describing the molecule. Okay, so here, right, we can do the whole structural formula, and again, if we take this, you know, C4H10O, okay, that doesn't tell us, this doesn't tell us who's bonded to who. This tells us who's bonded to who, right? Tells us which atom is bonded to which. Well, can we do that with using less space? Okay, well, if we look at this one here, okay, this also does, okay, this also tells us which is bonded to which. But uses less space. Right? All right. So CH3, okay, represents this. So this right here represents that part of the molecule. And then this part here is represented by the CH2, okay, and so on and so forth. So each successive part is represented by a shorthand, okay, and then the OH at the end. All right, now how would this change? Okay, I said if I drew the isomer here, okay, so I'm gonna copy this isomer, okay, And I'm going to paste the isomer here, but I'm going to make it smaller if I can. I don't know if it'll let me do it smaller. Oh yeah, it does. There we go. Okay, so I've made it smaller. So how would I represent this with a condensed structural formula? Structural formula. So here's what I would do. I would just do each kind of segment of the molecule as I did in the previous one. So it'd be CH3, CH2, and then when I get to this part here, it's CHOH, and then I have CH3 on the end. Okay, so my condensed structural formulas still give me the difference between these two molecules, but they do it in a little less space. Not too much less because it's still long, but it doesn't go branch off to the sides, right? All right. Okay, so that's structural models are the first way, or the structural formulas are the first way that we have of representing the arrangement of atoms, who's bonded to who. And so the next type of representation we use are what we call molecular models. They show the three-dimensional shape. Okay, so this is our structural formula. And again, the lines represent bonds, connections between atoms. Okay. All right, and so we have something called a ball and stick, this right here. Okay, so the ball and stick, ball represents an atom. All right, the color of the ball tells you the is related to what element it is. The size of the ball is related. It's scaled by how big the atoms are. Okay, and then the sticks represent the bonds. So the color of the ball, okay, is pretty, there's standard conventions. So generally oxygen is red, nitrogen's going to be blue, carbon will be gray, and then hydrogen is typically white. And then, let's see, another one is sulfur is yellow, and chlorine is green. Whoops. So we typically use these to represent organic compounds, which use kind of a limited number of elements. So, you know, there are, as you get to using more metals in your structure, we start kind of repeating the use of color. But usually when you use this kind of representation, you know what you're working with for a molecule. So the ball and stick, that's the type of model that you saw when you did the lab with WebMO and you were rotating it on the computer. And so you could see where things were closer to you or farther away and how they were projecting in space. Now the way we do this on a piece of paper, if we were drawing a molecule, is something called wedge and dash notation. So actually I'm going to do this. So the wedge, the black wedge, okay, means it's coming towards you. And then the dash, so these are called dashes, okay? Dash means it's pointing away from you, so that element is that atom is away from you. And then anything that is a line, okay, this is in the plane of the paper. So that's how we represent three-dimensional objects on the computer, okay? All right. Another type of three-dimensional representation is showing you a space filling. So this is a space filling model. And this is the balls used to represent atoms. More accurately represent the amount of space taken up by that atom. So these over here, they're just, you know, scaled down so that you can see lines as bonds, or bonds as lines. So the balls used to represent atoms more accurately represent how much space an atom takes up. Okay, so that is, you know, ball and stick versus space filling. So there's one other way so that we represent formulas like this. Okay, structural formulas. So, and this is used in organic chemistry. So in organic chemistry, we use another shorthand. Doesn't show the element symbols. And again, this is because in organic chemistry, we tend to use only a few elements. So this has 4 carbons in it. So the end of a line represents a carbon. Okay, so I'm going to do, so I have 4 carbons. So I have 1, 2, 3, 4. So I've got 4 carbons. So if I looked at each end of the line, right, I would have my 4 carbons. So I've got carbon 1, carbon 2, carbon 3, carbon 4. Okay. And so then hydrogens aren't shown. But we assume they are there to make sure carbon is bonded to 4 things. Okay. And then the last thing is that non-hydrogen, non-carbon atoms are shown with their symbol. Okay? So what that means is we would put OH on the end here, okay? And anything that's bonded to that non-carbon atom would be shown. So the hydrogen is shown there. And again, we assume that that carbon's going to be bonded to 4 things. So if I look at carbon number 1 here, it's bonded to 1 other carbon atom. So therefore, it must be bonded to 3 hydrogen atoms, okay? Whereas if I look at carbon number 3 here, it's bonded to carbons 2 and 4, so it must have 2 hydrogens. All right, so those are the different ways that we represent things. And these non-carbon, non-hydrogen atoms, this is called a heteroatom in organic chemistry. Because again, organic chemistry is the chemistry of carbon compounds, and so anything that's not carbon. All right, so let's talk about naming covalent compounds. Now, there is a whole language, okay, for naming covalent compounds, as particularly organic compounds, as the molecules get larger and larger. However, it's very complicated, and it's part of the language that you learn in other chemistry courses. For our purposes, we are going to name what are called binary nonmetal compounds. So binary, it helps if you're not writing with blue on blue. So we're going to be naming binary nonmetal compounds. Okay, so we're going to practice going from the formula to the name, okay, and vice versa. All right, so there's an interactive table in chapter 5 that you can refer to. So again, there are rules for naming compounds, and the rules get more complicated for larger molecules, but for binary nonmetal compounds, okay, these are the rules. Okay, the first word in the compound name is the name of the first element in the compound formula. Okay, first element compound formula, first word in compound name. Okay, if the compound contains more than one atom of the first element, we're going to use a prefix, okay, to indicate the number of atoms. Okay, so in ionic compounds, okay, so this is where we differ from ionic compounds. Okay, ionic compounds, you do not use number prefixes for anything because we're supposed to be able to figure out what the number of those atoms are based on the charges of the ions. Okay, so we have this compound here. Okay, the first word in the compound name is carbon. There's only one carbon there. Okay, in the second compound, the first element in the compound is nitrogen, but there are two of them. Okay, and so we would use the prefix di to indicate that there are two nitrogen atoms. Okay, and our prefixes are, our di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, and nona is 9, and then deca is 10, but we're not going to get beyond that because then your compounds are getting so big that you have to use the more complicated naming schemes. So, all right, make sure that this looks like an H. Okay, so that's the first word in the compound name, just the element name and a prefix if there's more than one of it there. Okay, so then the next rule is that the second word in the compound name is the name of the second element, and it's going to end with "ide," just like our anions. Okay, so this is similar to anion naming. Okay, and in all cases, we're going to use a prefix to indicate the number of atoms. Use a prefix for the number of atoms. Okay, so our compound, okay, there are two sample compounds. The second word is going to be sulfide for the sulfur, and because there are two there, we use the prefix di. Okay, in this one, we've got 4 tetra, and then oxygen oxide. Okay, so the compound name is just putting those together. So we have carbon disulfide and dinitrogen tetroxide. Okay, so again, these rules, our little friend Chameleon is indicating it's really important to remember these rules for naming covalent compounds. Okay, so these are covalent compounds. And binary nonmetal is, again, really just a specific way of saying a covalent compound that's only made up of two different elements. Okay, so these are the prefixes that I just wrote on the previous slide. So let's just do a couple of examples here. Okay. All right, so what's the name of this guy here? Okay, well, we've got 2 of the first element, so that's going to be di. And the element itself is nitrogen, so dinitrogen. And now we need to know how many oxygens we have. So we have 5, so that's penta. And pentoxide. Okay. So, did I put penta on my? Yeah, I did. Okay. All All right, so now that's going from formula to name. Now let's look at an example where we're going from name to the formula. All right, so we've got disulfur. So the symbol for sulfur is S, di 2, so we put a subscript of 2. And then fluoride is our second element, so that symbol is F, and deca is 10. So S2F10 would be the formula for that compound. Okay. All right, so let's do some more examples. All right, so I'm going to let you try these, okay? And I'm not going to record on the video, but when I post the notes, I will post them with the answers written so that you can check. So this is an opportunity for you to try and then check and see how you did. All right. Again, when we have carbon compounds, okay, we give them different names. There is, of course, a systematic way of naming, every atom in the compound, but there are a series of compounds that have, I guess, what we call more kind of common names. So there's kind of common names and systematic names. So some important, what we call hydrocarbons. So they're called hydrocarbons because they contain only hydrogen and carbon. And so these are called the alkanes, and so these names may look a little familiar to you. You've probably heard of methane, okay? You might have heard of ethane, definitely propane if you like to grill in the summer. Or butane if you have a butane lighter that you use to light candles or things like that. And then you'll notice we start to use prefixes when we get to larger numbers of carbons. Okay. All right. Some more other important covalent compounds are what we call the oxo acids. So these are acids that contain oxygen. And so things like perchloric acid, some of these are things that have been used as like disinfectants in the past. Hypochlorous acid, hypoiodous acid. These are things that maybe you're noticing have halogens in them. Okay, and you'll notice that some of them, the compound formulas look similar. Okay, so we have perchloric acid, and then we have, let's see, chlorous acid, okay, and chloric acid. Now, what's the difference between chlorous and chloric? Well, it's just the number of oxygens, right? So chlorous would be our HClO2, and chloric is HClO3. I'm not a particular fan of the us and the ick naming, but it is a key or a historical feature of chemical naming, okay? All right, so some important, what we call inorganic acids. Okay, we have things like hydrogen chloride, also known as hydrochloric acid. Okay, so these are the things that can dissolve in water. Okay, so HCl, when it goes into water, so I'm going to put a little arrow and I'm going to put H2O there to indicate that we're putting it into water. It breaks up into protons and chloride ions. Okay. Phosphoric acid, you may notice, has the polyatomic ion, the phosphate ion in there, right? And that's another thing that when it dissolves in water, H3PO4, it can lose a proton, and it'll be H2PO4 minus, okay? And so hopefully you'll start to see that things that we call acids, when they dissolve in water, give off protons. Okay. Some other ones that you've probably heard of are nitric acid, okay, nitrous acid. I believe that's laughing gas, isn't it? All right, and then there's sulfuric acid, which again, that's battery acid. All right. Okay, so again, we're going to kind of round up this by thinking again about how we want to know what naming conventions am I going to use, how do I know what's in my compound and how to represent it, right? So ionic compounds, remember, they are going to be things that are made of, that either have metals in them or polyatomic ions, or both a metal and a polyatomic ion. Our covalent compounds are going to have two nonmetals, right? And that's, you're going to look at your periodic table, and I'm going to say, is it made of of atoms from here? Well, then that's going to be my covalent compounds, right? Or do I have something from this side plus something from that side? Okay, so this and this is going to be ionic, okay? And so that's how you're going to be able to tell whether you have a covalent or an ionic compound. And that is it for chapter 5. So we made it through.